So what are Lebesgue-Bochner integrable functions? So a function f from a set X with a pre-measure mu will be called a mu Lebesgue-Bochner integrable if we can find a Cauchy sequence, say f sub k, of simple functions, well, to be precise, equivalence classes of simple functions, such that these simple functions converge to f almost everywhere. And we will denote by this notation here, the set of all mu Lebesgue-Bochner integrable functions on a pre-measure space X A mu into a Banach space Y. A tilde will denote the partition induced by the equivalence relation. And this equivalence relation is the equality almost everywhere. Okay, so these are the Lebesgue-Bochner integrable functions. So these are the limits almost everywhere, or these are the almost everywhere limits of Cauchy sequences of simple functions. Let us define a map, J, from the completion of simple functions into the partition or equivalence classes of Lebesgue-Bochner integrable functions as follows. So J of a typical element of this completion, and we have simplified it in this way. Okay, is equal to F. Well, technically, this should be an equivalence class, but again, as we said, we denote the equivalence class by a representative and treating the two functions are equal if and only if they are equal almost everywhere. Where for some subsequence f sub kj tends to f mu almost everywhere. Okay. Well, the convergence is guaranteed from the previous theorem. One can show that this is linear and it is bijective. So there's a one-to-one correspondence between the completion of simple functions and the equivalence classes of Lebesgue-Bochner integrable functions. So you could refer to the lecture notes for the verification of this statement. In this case, the mu Lebesgue-Bochner integral of f in this quotient space is defined as the limit as k goes to infinity of the integral of these simple functions. Okay, this f sub k here is the one corresponding to this equation. Of course, we need to justify the existence of the limit. This follows immediately from the fact that this sequence of integrals in y is Cauchy. And by applying the linearity and the continuous version of the triangle inequality, this is less than the norm of the difference in S tilde. And this, since this is a Cauchy sequence, this tends to 0 as k and L tends to infinity. Therefore, the sequence of integrals is Cauchy in y. And since y is a Banach space, it is complete. Therefore, we have a unique limit. So that justifies the existence of the limit. And in a similar way, one can show that the limit as k goes to infinity of the integral of the norm tends to the integral of the norm of the limit, which is f. Now, since f sub k is simple, one can apply the triangle inequality. So the integral of f sub k, the norm of it is less than or equal to the integral of the norm. And if we pass k to infinity, the limit of the left-hand side would be the norm of the integral of f. And the right-hand side would be, applying this limit here, would be the integral of the norm of f over x with respect to the pre-measure mu. And this is now valid for any f in this collection of equivalence classes. Likewise, we can now equip a norm on the equivalence classes of Lebesgue-Bochner integrable functions. So the norm here, which is similar to the case of simple functions, is the integral of the norm of f. Then one can show that this is now a Banach space. So you have a completeness. Recall here that with respect to the completion of a norm space, recall that the norm of these equivalence classes of simple functions in S tilde, this is equal to the limit, or I should say S bar, because we are now talking about the completion. This is the limit of the semi-norms of the representative. But of course, using, again, this equation here, and the definition of the norm in L tilde. So this is the same as the norm of L tilde. Norm of f in L tilde. Okay. With this, we now summarize the above discussion. we have in fact established the existence of a linear isometric isomorphism J between the completion of the simple functions in this pre-measure space with values in y into the set of equivalence classes of Lebesgue-Bochner integrable functions with respect to this pre-measure space with y. And moreover, the image of the equivalence classes of simple functions is dense in this space. So that's the summary of what we have discussed. So being an isometry is in fact obtained from this equation. Hence, based on this theorem, we may identify elements of the equivalence classes of simple functions with the set of equivalence classes of Lebesgue-Bochner integrable functions. So in this case, we may say that the set of simple functions is a subset. Okay, by this, we mean precisely with respect to this mapping. After identifying the pre-image and the image of this mapping, and this inclusion here is dense. Okay. So simple functions are dense in the case of Lebesgue-Bochner integrable functions. So since there is a one-to-one correspondence between these two spaces, if one is a Banach space, then the other one is also a Banach space. Indeed, that is because the distance preserving nature of this map, J. So therefore, we could simplify the characterization of the completion of the simple functions in this way. So we can think of the completion of the simple functions as the equivalence classes of Lebesgue-Bochner integrable functions. With this, we now again remove the tilde or suppress the tilde in the notation. In other words, for simplicity, we will ignore this tilde here but keeping in mind that these are equivalence classes. As we said, we treat the equivalence class as the same, or we treat the equivalence class with a given representative, again having the convention that two functions are equal if and only if they are equal almost everywhere. So in the previous discussion, we have shown the Chebyshev inequality for simple functions. As mentioned a while ago, it is also valid. The Chebyshev inequality is also valid for Lebesgue Lebesgue-Bochner integrable functions. So let us establish the Chebyshev inequality for Lebesgue integrable functions. So for every positive epsilon and for every Lebesgue integrable function f, the outer measure of the set where the norm of f is greater than epsilon, is less or equal to 1 over epsilon times the Lebesgue integral of f over x. So the idea here is to apply the Chebyshev inequality for simple functions, and noting that Lebesgue integrable functions are the limits almost everywhere of simple functions. So let's start with the definition of a Lebesgue integrable function. So there's a Cauchy sequence of simple functions in this pre-measure space with values in y, such that we have convergence except on a set n for some n subset of x with outer measure 0. So we have a convergence except on a set having outer measure 0. Adapting the proof a while ago up to a subsequence, we can assume without loss of generality that the norm of the differences is less than 1 over 2k. Now, let us take a particular x not in n, take a delta less than epsilon, and the norm of f of x is greater than epsilon. Now, if the norm of f sub k of x is less than or equal to delta, then applying the reverse triangle inequality, the norm of the difference should be greater than or equal to the difference of the norms. Since the norm of f of x is greater than epsilon, and the norm of f sub k is less than or equal to delta, then this is greater than or equal to epsilon minus delta. Applying the same method as before, computing we estimate the norm of this difference. Take note that f sub j of x tends to f of x. So we can write this in terms of this limit. And then by adding and subtracting terms and applying the triangle inequality, this is less than or equal to the sum j from 1 to k, j from k to infinity, I should say. Then f sub j plus 1 of x minus f sub j of x. And there should be a k there. Okay. Now, if you notice here, this implies that for some sufficiently large L, greater than or equal to k, X would be an element of this set, AKL, defined to be a partial sum of the tail. So the sum is from k to L, j plus 1x, f sub j of x, greater than epsilon minus tilde. And why is that the case? Take note that if based on this inequality here, this is greater than epsilon minus tilde. So epsilon minus tilde would be less than, strictly less than, this sum here. So say that sum is located on this part. Okay, so if I denote this by, let's say, AKL, take note that AKL tends to star, okay, as L tends to infinity. So because this is only a partial sum of the tail. So if we make L large enough, we are getting closer to this part. Okay, so this means that X would be, or this partial sum here would be greater than this epsilon minus delta. Okay. So we started with this assumption. We have shown that it is in a KL. Of course, if X is not in N. And with also this assumption. So combining all of this, we could say that the set where the norm of f is greater than epsilon, well, it is possible that it is in N. It is possible also that it is in the set where fk is greater than delta. But if the point is neither in N, neither in the set where the norm of f sub k is greater than delta, then we have these two conditions, and those two conditions implies that X is in E sub KL for some L greater than or equal to K. And that way we could say that it is in the union of AKL, L greater than or equal to K, so L from K to infinity. We can now take the outer measure and applying the sigma subadditivity of the outer measure. This would be less than or equal to the outer measure of N plus the outer measure where the norm of fk is greater than delta plus, okay, the a, k, l are increasing with respect to L. So this is the same as the limit of the outer measure of A KL. Since the set here lies in the algebra, we could replace this by just the pre-measure. Okay. Now, we apply the fact that this is 0. And then here, the second term, we apply the Chebyshev inequality for simple functions. Since f sub k is simple, we can apply the Chebyshev inequality. This is 1 over delta times the integral of f sub k d mu. The second term would be, again, applying the Chebyshev inequality for simple functions. That would be for a KL, take note that the lower bound is epsilon minus delta here. Hence, we would have the following inequality. So this would be epsilon minus delta, and then the integral over x j k to infinity So we take the limit first. Let's do this slowly. The limit j from k to l, the integral f sub j minus 1 plus 1, f sub j, take the norm, integrate over x, okay? And again, this is less than or equal to 1 over delta f sub k d mu plus 1 over epsilon minus delta. In here, you have an infinite series. If you pass L to infinity, and by construction, the distance between two consecutive functions is 1 over 2j. Okay. So now we set k to infinity, or pass k to infinity. So this tail would converge to 0 as k goes to infinity. And this one tends to the integral, and we have seen this a while ago, of the norm of f as k goes to infinity. So therefore, we have the following. So looking at the left-hand side, so that's the outer measure of the set where the norm of f sub k is greater than epsilon, is less than or equal to 1 over delta times the integral of the norm of f. And this is true for any delta positive and less than epsilon. Then we take delta go to epsilon from the left. So with this converges to 1 over epsilon over x times the norm, the integral of x of the norm of f. And this is the Chebyshev inequality. Okay, the second remark is the following. If we have convergence of a sequence f sub k to some element f in the space of Lebesgue-Bochner integrable functions over this pre-measure space with values in y, then there exists a subsequence of Lebesgue-Bochner integrable functions such that we also have convergence almost everywhere. Okay. So take note here, the difference with the previous theorem is that these f sub k's are not necessarily simple functions. They are, in this case, Lebesgue-Bochner integrable functions. So let us look at the proof. Doing the same business as before, let's take a subsequence wherein this difference is 1 over 2j. And then we relabel the indices. Given a positive epsilon, we define n sub epsilon to be the set where the limit superior as j goes to infinity of the distance of the limit and the terms of the sequence is larger than epsilon. By applying the definition of the limit superior, this is in fact a subset of the union j from L to infinity. L here is any positive integer of the set where the norm of f times f minus f sub j is greater than epsilon. Now, thanks to the Chebyshev inequality, applied to this set here, since f minus f sub j is also Lebesgue-Bochner integrable, the outer measure of n sub epsilon would be less than or equal to the sum j from L to infinity of 1 over epsilon times the integral of the norm difference d mu. And applying this assumption here, we can estimate this as 1 over epsilon times the sum L from 1 up to infinity of 1 over 2j. And again, this is a tail of a convergent geometric series, then this tends to 0 as j tends to, or as L tends to infinity. Therefore, the outer measure is of n epsilon is equal to 0. Okay. Since the sequence where we have non-convergence to 0 or to f is a subset where is a subset of n epsilon for any epsilon greater than 0. Take note that if you do not have convergence with respect to f, then your limit superior must be positive. Okay. So since this is the case, this implies that applying the monotonicity of the outer measure, and since the outer measure of the larger set is 0, then the outer measure of the smaller set, that is the set where we do not have convergence, is 0. So in other words, we have convergence almost everywhere. So to summarize the two remarks, the second one, so if you have a convergent sequence in the space of Lebesgue-Bochner integrable functions, then you can find a subsequence wherein you have a convergence almost everywhere. And the first one is that the Chebyshev inequality is also valid for Lebesgue-Bochner integrable functions. So in the next lecture, we will connect the concept of Lebesgue-Bochner integrable functions with measurable functions.